I'm going to tell you a little bit about using deep learning to solve routing problems. My focus is going to be on the search heuristic side. We've already had some introductions to this idea of using ML to solve routing problems from Andrea and Wouter. And I don't want to repeat anything, of course. I want to try to move in a bit of a different direction with it, give you an idea of how this stuff works. Especially, we have a lot of OR people who maybe haven't used these techniques or only seen paper here and there about it. I'll try to give you a little more insight and point you to some nice code and tell you a little bit about at least where I see the current challenges that are facing us, and maybe also put things a little bit into perspective. So we'll start with motivation and manage your expectations a little bit. We don't want to get too exuberant here about machine learning. I'll tell you a little bit about routing with ML, and then describe a few different search techniques that you could use to do your, basically, to do the search. I guess that for an OR audience, I don't have to really justify the idea of search. I mean, everyone in OR kind of says, yeah, well, why wouldn't I do search? In the ML community, I feel like right now there's a lot of people thinking about this sort of, let me just take a neural network and generate a solution. It's like, well, no. Like if you could just take a neural network and generate optimal solutions, I think this would say, okay, it's not a proof, but this would probably say something about P equals NP, right? I don't really think it'll ever be possible to just go and do that, but who knows? Maybe someone can prove me wrong. It would be great if they could. And thanks to all my co-authors, Young Dae, who's here, Andre Hotung, who just finished his PhD with me, and many others. This has been an interesting ride so far. All right, so you already know this idea is you have to have a robot. If you talk about deep reinforcement learning, there has to be a robot somewhere in the slides. Otherwise, I think you get a fine somewhere from the ML authorities. The NeurIPS people come and they charge you money. So the idea is that you make decisions and receive feedback from an environment. And our goal here is, at least here, I changed the presentation. It used to be combinatorial optimization. Now it's routing for you folk. But I mean, I would argue my goal is really to solve combinatorial optimization problems. It doesn't have to be routing. We've done scheduling problems. We've done container stacking problems. You can really do anything. The goal is to solve them through reinforcement learning. But today, we'll just talk about routing. Now, let me move that out of the way. Maybe I could talk about a few advantages and disadvantages, because maybe this expands a little bit on some of the previous presentations. So, because I think it's a legitimate question to say, well, why do we even want to do some ML here for this? Because I think there's a pretty good argument that we have really good heuristics, traditional. I call them traditional. It's like artisanal water or something, like traditional OR heuristics, from the old country. The traditional OR heuristics to solve routing problems are really good. And admittedly, we don't beat them. And so it's why do we even care about this? Why should we even try to use RL here to solve problems? Well, I think there could be some advantages. One of them is that I hope that these techniques in the future could lower the barrier of entry to solving some kind of OR problems. In other words, it could sort of turn solving an OR problem into more of a data science problem. If you talk to data scientists or train them, we train them in Bielefeld with some optimization background, but a lot of data scientists leave universities not knowing anything about optimization or operations research. They know nothing. But they have the arrogance to think that they can actually solve these problems, and they can't. So nonetheless, it'd be nice to give them a tool that they understand. I mean, basically by putting a combinatorial optimization problem into an RL sort of framework, you kind of give them a recipe they know how to cook. And that might allow a wider audience to solve OR problems. And that could have advantages, especially for, let's say, smaller companies that can afford a data scientist but don't have any OR people. So maybe there's an advantage there. Another advantage, and I think this is really the bigger one, is that you can customize heuristics for the instances at hand. And so my background is actually more in algorithm configuration and algorithm and parameter tuning. So for those folks having some issues with parameter tuning, just talk to me. I have 2 PhD students only doing that. And what we've seen in the past, especially in satisfiability problems and MIPS, is that the algorithms can be very specifically configured to instance sets. So SAT solvers that work well on randomly generated instances do not work on industrial instances and vice versa. They're different solvers, and they require vastly different parameters to solve those different problems. And so if you have some company somewhere, you should be configuring your algorithms to the instances that you have. And so at the point where you don't write a traditional OR approach and configure it, why not learn an approach that's specifically tailored to your data, right? It doesn't have to work for anybody else's. It just has to work for yours and automatically adapt itself to the drift. We saw some drift early on, I think, with Andrea's presentation, we had sort of this idea of ML drift. It has to automatically adapt then to the changes that occur in your data over time. There are some disadvantages, though. The learning phase is computationally expensive. There's no question, learning these things on the GPU, or if you do algorithm configuration on a CPU, it's expensive. But then again, it's kind of a one-shot deal. If you amortize that over a number of years, it's not that significant, especially not now. But, okay, it's an expense. The algorithmic interpretability right now, especially of the deep network stuff that we do, I would argue is terrible. Why does the deep network say to go here? I don't know, it just said that. What do I know? Don't argue with the deep network, it knows what it's doing. Well, no, not always, right? They make wrong decisions, and there's no way to know why. Now, this might not be such a big deal because a human planner maybe doesn't know what they're doing all the time either. So this is one of those trustworthy AI arguments where you kind of, are we holding the computers to a higher standard than ourselves? Maybe we are, but maybe we should hold ourselves to a higher standard too. At any rate, right now, the algorithmic interpretability is terrible. I hope we can improve this over time. Probably the only way to do this is to throw away the deep networks and use something else, but I don't know how to do that yet. Nonetheless, I'm throwing it out there as a problem that maybe we need to deal with and a clear disadvantage of these approaches. All right, let's manage the expectations here. So you are expecting the Lamborghini, but I'm very sorry, you get a Toyota Camry. So this is not a bad thing. This is, that beautiful car there. I had this car in red. That was my first car. They run well. It works. It's not as fast as a Lamborghini though. Like the HGS algorithm, that's Lamborghini, right? And what I'm going to show you with the deep learning is more of like the Camry. Like it just works. In other words, you can't query the model, get an optimal solution. I can't solve any routing problem a user provides. As soon as the side constraints move out of whatever I've trained for, we're completely done. I can't scale to any problem size. I just can't. The deep networks, we're getting better at it, but they don't. The reality is that you query the model and you get a solution. It's not necessarily great, but it's usually okay. And if you do a little search, you can make them really good. We solve simple classes of problems. Maybe our dirtiest secret of all is that the deep reinforcement learning we've been doing has really been on simple problems. Nothing against TSP and CVRP, but finding feasible solutions to these things, not exactly hard, right? I have a TSP demonstrator I show to my students. My 5-year-old gets good solutions on that. She's great at it, but she doesn't find optimal ones, right? And of course, if I gave her a problem where feasibility is difficult, she's not going to be able to solve it yet. We're working on it. It's going to be an optimizer. We'll see. And so, we have easy classes of problems here, if you ask me. Not computationally easy, but sort of easy-ish. And so when the side constraints become harder, more complicated, more of them, we don't have any techniques for that yet. Can't do it. And if anyone tells you that we do, I'd like to know what they're doing because I haven't seen it. We don't scale that great. We don't really scale that great at all. When the instances become too big, especially the attention mechanism that's used in the deep neural networks, it's quadratic in the size of the problem, so yeah. Okay, so how does this whole thing work then? Because we haven't really seen any encoders, decoders, that kind of stuff yet, so I want to show you at least a little bit about how this works. The basic idea is that if you give me a routing problem, I'm going to encode it into some kind of embedding. So I'm going to encode it. This is like doing some feature. Like if you're doing some classic machine learning, you compute some features about your problem, and that describe this problem for your machine learning model. We take that. This is, of course, very compressed. We take that and use a decoder to then make decisions. So I have then, so if you remember the nice animation from Wouter, how do I then decide which which node I go to next. These little bars here represent the probability that I should pick the node based on what the network tells me. The decoder basically makes those probabilities, and then I sample actions or take the argmax or something based on that, and I go action by action. So I go from here to here and sample again, and so on. And so you can kind of see that the two key components are, well, how do you make a nice encoder to basically take your instance and your nodes in the instance and generate features about them? And then how do you use those features to make decisions? Now, what's cool about this encoder-decoder architecture, because this is only one possible architecture. There's lots of different ways to solve routing problems using DRL. This is just one. What's nice about it, though, and what really makes it, makes it, I would say, superior to other architectures out there right now, is that it accepts variable-sized inputs. So at the beginning of this whole type of research, this deep reinforcement learning, you had techniques that would basically accept a 50-node CVRP, and they could solve 50-node CVRP. They could solve 49 because that's just basically sort of giving it an empty node. They can't solve 51. Too big. Doesn't fit. Not so satisfying, right? Like, it's not really so good. So this is nice because you can give it a 50-node CVRP, give it 49, give it a 51. It doesn't really matter. Obviously, the further away you go from the distribution you trained on, the worse the performance gets, right? Like, it's just not going to work as well because it doesn't know how to solve those types of instances. But nonetheless, it can do it, and it can give you something. There's a couple key papers for that. This one you've seen the reference for. I want to also point out Young Dae's paper. Pomo kind of extends this in a really nice way, dealing with symmetries, and the source code's available online. And I think, basically my PhD student, Andre, has now published. He just likes playing with this source code a lot. So you can do a lot of things with Pomo. And our source code's available too when we're speaking about reproducible AI. Okay. So let's go back to, for the OR crowd also, and discuss maybe a couple other topics here that are important to think about, namely, why reinforcement learning? So I've been talking about reinforcement learning, and I haven't talked about supervised learning. I want to give a little bit of a dichotomy here between the two, so you can understand why are we doing reinforcement learning. So if I do supervised learning, in other words, the problem here is that if I do supervised learning, I need to have a data set that kind of tells me, what are the correct places to go next. That means I have to solve the instances that I have in advance. And one might argue, well, it's no big deal, right? We take HGS, you take a MIP, you take something, and you solve them. Well, okay, but what if you have a new problem? Do you really want to go and write a heuristic for it and then do this whole learning stuff? Like, for me, it feels kind of weird that, in other words, that the supervised learning has its place, and I'm sure there's there's potentially good uses for it in this field. But right now, what I don't like is that you need to have some traditional OR approach, or else the whole thing falls apart. You cannot learn anything. But it would speed up learning potentially, and can give you some really nice solutions that maybe you wouldn't find in reinforcement learning. Why is reinforcement learning nice? You don't need any existing algorithm, right? You just have to define your problem, and then try to solve it a bunch of times, and you learn as you go. Of course, the downside is that the approach starts out really stupid and has to become smart. And one of our, let's say, the disadvantages that we have in this community compared to maybe the large language models and those folks, they have something they call foundational models. So they have these models that are just really well trained on lots of text, and they take them and they're like, okay, well, I want to learn about like finance. I want to do some finance, like have a really nice model just for finance stuff. They take a general model, foundational model, train it on finance, works great, and it's really easy. It's not much extra training. We don't have that, although can I propose Pomo as being like maybe the closest thing we have, at least in routing, to a foundational model. But in principle, we don't have some model you can take and like, okay, now I'm going to do scheduling. Now I'm doing assignment problems. Like we don't have that. We have no foundational models, which means that, at least in reinforcement learning, for the most part, you're starting from stupid and trying to get smart, rather than starting from smart and trying to get smarter. That makes things slow. Okay. Let's try to generate a solution for the CVRP using the components that I've showed you so far. Basically, we're going to compute some features for each node. Now, I'm in a Euclidean setting here, which I'll admit is like kind of unrealistic, but it's the best we mostly can do now. So I have XY coordinates for all the nodes. Those are basically my node features. I'd put the XY coordinates in. Maybe if I have a demand or something for these nodes, if I'm on the CVRP. If you have time windows, you could put the time window in as a feature. I mean, it depends on your problem. You can put in whatever features you have. I'm going to stick those in an encoder. And of course, some versions use the arcs as well. I'm just going to keep it simple and just look at the nodes here. So we put all those in. I get an HI for every node, and I can combine those together to an H. So this H describes, these are the features for my instance, and for each node I can also have some features that describe the node itself. Then I'm going to just take all these guys and stuff them into a decoder for each of the nodes. So this is the HI part. So basically I'm here right now at the depot. That's my H0. So I say I have one piece of this vector saying where am I? And then I'm going to ask, like, should I go here? 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 And so on. You can see it's not the most efficient thing. The good news is that this is highly parallelizable. So I can actually ask, should I go here, for all the nodes basically at the same time, thankfully. Otherwise, this would be really slow. But GPUs are great at parallelism. And I pass in this instance feature as well for the whole instance to kind of give some, let's say, global information. Then the decoder gives me this UI, which is a score for the node. Take all my UIs, I do something, the softmax, which basically builds a probability distribution out of the scores, and then I can decide what to do next. So maybe I go here, because that one has the highest probability, and so on. And that's the basic structure for how this works. And you repeat this process, ignoring the masking nodes that you've already visited or that are infeasible or whatever, and you do this until you're done. OK, the problem, though, is what if the solution you made isn't good? Like, what if that's a bad solution? Well, that's when search comes in, right? Originally, a lot of people were using sampling, but sampling doesn't really, well, it's random, right? It doesn't really get that far. Now, if you try to use some kind of intelligent high-level heuristic, then we can get somewhere. There's a whole bunch of different techniques with different trade-offs. Usually, we want to try to be parallelizable. We'd like to use a GPU to the fullest extent. What we don't want to do is iterate sort of between the CPU and GPU, because this is unfortunately quite slow. There's latency between CPU and GPU, although the new MacBooks are much better than, actually the Apple hardware is quite good at that, but still you have a slowness of going in between. So you'd like to stay kind of on one or the other. In other words, GPUs are really good. So I think of the GPU as like a marching band. CPU is like, I don't know, someone who's the Renaissance man. CPU is like one guy who's like really good at everything. The GPU is a marching band. Like, everybody marches together and solves a problem together, but everyone has to do the same basic thing. Like, everyone's playing an instrument and playing the same notes. If everyone starts doing different things, the GPU can't solve anything. Question?
Just going back, are we basically thinking about this solution being the seed that local updates are going to be used to somehow fix it up? Is that the search part?
So I'm thinking search like, I'm just going to generate new solutions, for example, or I'm going to, you could, of course, do a local search on top of that somehow. We don't have so many good deep techniques for that. There are a few, but.
You get the solution, but we're not going to use it in any way.
We will. We will, I promise. One second.
But not as a
yeah. Like, you don't have to, but you should. That's basically my argument, because if you don't use the solution, you're just doing sampling, right? You just keep generating new stuff, and we'd like to learn something on the search side. So in other words, I think that the ML view up until recently was, let's do our learning offline, and then we can solve things. What I'm saying here, and others as well, is, hey, let's learn something online as well when we're actually solving the problems, because we have more than 0.1 seconds to solve these, right? Like, we can actually take a little more time. And that gets us to neural large neighborhood search. That was one of the first methods we proposed at ECI a few years back. The insight is that, OK, I mean, if you want to solve routing, for example, large neighborhood search has always been just a really good heuristic at it, right? I mean, OK, maybe it's not the best anymore, but it's still been really good for a long time. So the contribution here is to make a repair operator based on a learned deep neural network that can construct solutions and based on after a destroy step. So our destroy step is very basic. We wanted to try to keep it as simple as possible. We just remove a part of the solution at random. For example, a point-based destroy. So just, whatever. Just take some part of the solution, throw it away. Then we apply an argmax policy of our model. So right, instead of sampling, I'm always going to take the action or the node that has the highest probability. And I just basically do that until I have the whole a whole route fixed again. Of course, here, for example, I have to fix that up. You have to go route by route and fix them. And then you just iterate the destroy and repair until convergence. Code is here. It's really that simple. You train your model offline using supervised learning or reinforcement learning, and then you just do this destroy and repair iteration, and it actually works quite well. So I can show you some solutions on the, and so we generated some instances with this this X generator, and it's a little bit old. That's why we have the gap to UHGS and not to HGS. So what you can see here, though, is what's important is, so for example, if I just take a sort of standard LNS, whatever that means, so I admit that, fully admit that, we tried to make a nice LNS there as a point of comparison, but anyone can go and poke holes in that and say, well, this LNS could have done that, could have done that, could have done that. I fully admit that. We just wanted to see if our operator made any sense at all. Was it making good decisions in the repair? And for the most part, we beat the LNS everywhere. LKH3 is, as a point of comparison, also we actually are able to do better than it on most of the categories, not all of them, but most of them. And the amount of CPU, the amount of wall clock time, sorry, it's not CPU time or GPU time. We're just comparing on wall time here because, well, as we saw already from Luca's presentation, it's not exactly easy to actually compare things in a really fair way. But basically, the times here are sort of as fair as we can get, I would say. But in some cases, LKH3 really has less time. But it just decides it's done. So what can we do? And I should note, this is the gap to UHGS, right? UHGS just eats our lunch on basically everything here. It just totally kills us. And HGS is even better. So yeah, we're not there yet. How can we do better than that, though? NLNS is a nice method and all, but it's a bit expensive. Basically because of the destroy and repair are doing exactly what I told you not to do, which is sort of iterating between CPU and GPU. Efficient active search, on the other hand, adjusts the weights of a trained model with respect to a single instance at test time using reinforcement learning. So this active search is a really nice method proposed all the way back in 2016 with one key problem. It's so expensive it doesn't actually work. So the idea is that you fine-tune your model when you're given an instance to solve. You basically just you solve it and then backpropagate the information through. You do reinforcement learning. But it's too expensive to update all those weights. So we propose 3 different modifications. I actually won't go through them. They're in the slides, and you can have the slides after, and you can look at them later. We propose 3 different modifications where you basically will update a single layer, update the embeddings. So basically you're going to change the embeddings based on what you're seeing, or change a layer in the decoder. Or if you don't want to do backpropagation, you can actually just update the action sampling directly. And in my opinion, the reviewers always said this didn't make sense, so maybe what I'm telling you is just wrong. But I always feel like this. That updating the action sampling, it reminds me of kind of like ant colony optimization, right? Because ant colony is making these probability distributions over what you do next, and changing that sort of output space feels to me like ACO. But everyone says, I don't know. The reviewers always told me it doesn't make sense. So okay, maybe it doesn't make sense. Whatever. Maybe I have to admit that at some point. The code for EAS is available. It's based on POMO and improves performance quite a bit. And all 3 strategies are implemented for you. Not one single strategy works the best. We don't have really good guidance there on that. I'm going to just jump over that. So further enhancing search. So we have a latest paper with Youngdae and his group at Samsung about simulation-guided beam search. And what this is starting to get into the challenges here. Basically, the insight is that these models, especially POMO and others, DACT as well, they make stupid mistakes with high confidence. They can do 19 out of 20, you have a CVRP and you have to, a route of length 20 or something. 19 of those moves might be optimal, but the 20th one or the 15th or somewhere in there is so incredibly bad. And the model just thinks it's the perfect move. Yeah, what do you do? What are you supposed to do here? So I call this this kind of a confidence mismatch. So you don't really know. D was maybe the better move to do, but the model thinks it's so bad. And that means that even in a search procedure, you don't really see it that easily. You don't really know it's there. So the idea is to use beam search with simulations to try to overcome this overconfidence of the model. And here's a pretty picture. Without going into like a ton of detail, basically you're going to use the model to first prune out which next nodes seem reasonable. Then you're going to use simulation. So you're going to use the model to try to do a look ahead and basically price out those nodes that you've pre-selected, and then just take the best ones of those. In other words, by pricing them, you might see that, oh, well, actually the model made a mistake, right? The model thought this node was the best, but actually this one through a look ahead looks better. And so I'm going to look over here instead with the beam search. And beam search is really great on the GPU. I know like beam search hasn't been a real big method in the OR community so much, but beam search actually on GPUs is really nice because you have a fixed width, and that means that that's the marching band, right? The marching band is this wide, and the marching band just marches through in its beam search, and it's very fast. And you can use EAS too. So let me show you just some results on that before I go into the final challenges of this and wrap up. Basically, with efficient active search, you can get, so this is on the CVRP, we have a test set of 10,000 instances, size 100, and we have some generalization, so try to make it harder, size 150 and size 200 over here. EAS has a gap of 0.35% to HGS. Using SGBS, you can get that gap down to 0.2, or if you run it even longer, so for 30 hours for this whole data set, you can get it down to 0.11%. So it's a very low gap to HGS by running this thing for a long time. And what's really nice about this, EAS and SGBS in general really allow you to go to larger sized instances without retraining. This is without retraining. This is just going to these bigger instances. We have 0.6% to optimality, 1% gap. And if you look at sort of other methods, including our own like NLNS up here, they work fairly well when you keep the size of the instances in the test set and the training set the same. But once you go to something bigger, they start to really break down. So this is a nice advantage of doing this reinforcement learning online, doing the search at test time. It helps a lot. You can do it on scheduling too, but who cares? No one cares about scheduling here, right? This is about routing, like scheduling. Okay, further challenges. There's two big further challenges I see right now. One of them is about problems with feasibility, as I mentioned at the beginning. These sort of, our problems here are sort of unrealistic and trivially feasible, and that's too easy. Complex side constraints, combinations constraints are widely ignored. I have a new project, so if you have someone who's maybe looking to do a PhD and would like to come to Bielefeld, Germany, I have a position that's opening in like the next month or so on this DFG project I just got, and so I'd really like to have someone who's interested in this stuff, so please pass this on if you have anyone who's looking. We're going to be doing just this. We're going to try to figure out what do we do when you can't just make a feasible solution trivially. Search diversity. So deep models are great at intensification. Diversity is difficult. So I'm going to give you a short look at our ongoing work. Basically, what we've found is that you need to try to train models to be more diverse from the start. And that means that instead of being so confident that a single thing is the right solution, we need to find ways of making models suggest alternatives in order to better search the space. So here what we did was using POMO. Here we have POMO trained with a diversity mechanism, which I don't have time to describe. But basically the improvement here is quite, okay, these are like really small numbers, but you know how that is on routing. Like on a large data set, we actually are getting a nice improvement here by enforcing diversity during the training. In other words, we say to POMO, you should not become overconfident on certain moves. Don't become overconfident. And I think by removing that overconfidence, we're able to find better solutions. But this is still very preliminary. Like even LKH3 is like down here in terms of performance. This is only a few samples and stuff, so it's not that far along yet. But I think the initial results are very promising, and I feel like diversity is kind of definitely a promising area to go in. All right, so to summarize, algorithms can be learned for solving specific data sets, so this is really good news. learned methods have almost reached the OR state of the art, but they're not there yet. There's a few problems where we have beaten the OR state of the art, like container pre-marshalling, but of course everyone would say, well, okay, who cares about pre-marshalling? What is that stupid problem? Yeah, fine, whatever, okay. It's not that important, I realize. But we have a paper that does better than our own state-of-the-art heuristic, a biased random key, GA in fact. So search is an essential component of any learned technique. And I think it's really important. So if you're going to do deep reinforcement learning for routing, for optimization problems, you've got to use search. And just try to remember that when you go at these things. So we have papers and source code available for everything in this talk. And yeah, thanks for listening. Hope we have some time for questions.
I think we have time for a couple very quick questions.
Question. Do you try to solve any practical problems?
Sorry, what kind of problem?
Any problems from the industry?
Industry. No. No.
Some
No.
experience to see what
No, I mean, that's sort of the problem. Like, you know, if any company came to me and said, like, hey, should we use this technique? I'd say no. Don't do it. It's not ready. It's not ready. That's the honest truth. We have some interesting problems from a local company making kitchens, and we have some a company doing like some ship stuff, routing of ships and things that I would like to try these things at some point, but it gets back into the sort of feasibility issue. Like we just can't. It's just not quite there yet.
Sometimes these companies, they have already some solution.
Yeah.
And you want to take advantage of that solution to go to the better.
That's a good point. Because yeah, they have heuristics already. I mean, the kitchen company already has a way of delivering their kitchens, right? They already route like 4,000 kitchens every week. I mean, they can do that. So yeah, we'd have a nice data set there. It's a next step. Yeah, definitely. We'd like to see how that goes.
One last quick question.
Yesterday we had a talk by Luca Kors about the issue of how the machine learning algorithms are tested and compared with OR. And for example, we have proposed a set, Thibault and I, we have proposed a set with 10,000 CVRP instances generated from distribution that matches very well reality. It took us years to build. All of those instances have optimal solutions known. And why people in this area do not use those instances? They always generate their own instances.
It's because of the RL side. I mean, actually, honestly, I've been talking to Andre, the PhD student, a lot about this because I would like to use this stuff too. On the training side, you definitely need a generator because,
yes,
I mean,
for sure.
right, but it's true. On the testing side, we should be using those and we've been doing it wrong, and I agree totally. It's
for sure, for that, for training, you should generate. Okay, but okay, we have a test size with 10,000. You can compare with the optimal, not with LKG3, which is far from state of art.
Yes.
Okay.
I mean, we barely beat
here
that
in this
though, right?
room, we have 6 heuristics that are better than this. But I'm not against this, of course. All you present is very fascinating, and but I think it's very important for the area to have standards. We should be able to evaluate things, to compare things, and a very important thing is to use the same data set. So the same data set, not for training, of course. You are not going to overfit.
Right.
After you do the training, if different people use the same data set, it's a very large data set, it's a very diversified data set, and then we can actually make our progress. We can compare different approaches.
Yes. Can I just tell you, I feel held hostage by this data set in a sense. Like, I hate this data set. It's a bunch of random garbage. If you don't use it, they will reject you, right? Like, so, okay, I am a hostage of this crap data set. I agree with you completely. And actually, so part of this project, part of it, and if anyone wants to help with this, like, please feel free to contact me. We are going to make, let's call it, like, you know, in RL, they have this thing called the gym. We are going to make a combinatorial optimization gym for these types of problems where we can then take, you know, these instances, good instances for the test set, make a nice generator for them, and have these things standardized that you can just take, download, and pip. That's where we need to go.
We have a very good generator. In Python, you can know.
Yeah, we won't reinvent the wheel. We just use it.
Very good generator that was tested over the years. Okay, there are many.
it all needs to be together in one package, you know, for the
Yeah.
for the ML people, and that's where we need to go with this. So that's what we're hopefully going to do.
Okay.
Well, that's great. Thank
Good.
you.